Just total destruction. Everything we've grown up with and lived our family with was gone.
All the old houses that were along the beach, they were all gone.
But now there's just nothing, still, even after 2 years.
I'm meteorologist Dr. Bill Williams at the University of South Alabama. The year 2005 was the most active hurricane season on record. During that year, 27 named storms roamed the Atlantic Basin, with several major hurricanes reaching the Gulf of Mexico. One of those storms was Hurricane Katrina, the most destructive hurricane in U.S. history. On August 29, 2005, Mississippi, Louisiana, and Alabama experienced a day that will never be forgotten. Without question, Katrina left an unprecedented legacy of destruction. However, in the months following Katrina, valid questions remained about the causes of the massive path of damage that stretched from coastal Louisiana to New Orleans, then eastward for more than 120 miles across the Mississippi and Alabama coasts. Even after moving inland, Katrina's winds produced severe damage as far as 200 miles to the north. Why was the storm so bad? Several prior storm assessments have said the winds were not extreme as Katrina came ashore. If that were the case, then why did Katrina produce Category 5-like damage over such a large area? The Coastal Weather Research Center, working with scientists from the University of Wisconsin and Mississippi State University, has conducted an extensive analysis that answers these questions. Through post-storm research, aided by the use of microwave satellite technology, we now understand why Katrina was so massive and destructive. This research shows clearly that Katrina pounded the Gulf Coast for many hours with hurricane-force winds before the storm surge came ashore. Several factors came together to produce this wide path of destructive winds, as well as the ensuing storm surge. These factors included the track of the storm over the warm waters of the Gulf Loop Current, the shape of the coastline, and the violent winds circulating around Katrina. Together they combined to create an extraordinary environment for a record-breaking hurricane. The result was a monster storm with a double eye wall with extended periods of northeasterly and easterly winds, collapsing cores that forced strong winds to the ground, and numerous tornadoes and other rotational wind events. Prior to this research, almost all of the post-storm wind analyses of Hurricane Katrina failed to take into account the existence of collapsing cores and the many types of rotational winds. As a result, wind speed maximums on the Mississippi coast were shown to be far less than what actually occurred. Let's revisit the Mississippi Gulf Coast for a detailed discussion of what science has revealed about Katrina. Despite Katrina's legacy of destruction, Katrina did not have the classic track of the great storms. Instead of forming off the African coast and taking a long curving sweep across the Atlantic, Katrina formed over the Bahamas just east of the Florida Peninsula on August 20th. Then 2 days later, it became a named storm when a cluster of thunderstorms rapidly organized. The storm intensified into a hurricane on August 24th as it approached Florida's east coast. The next day, Katrina made landfall as a Category 1 storm on the Saffir-Simpson scale. However, high pressure along the east coast of the United States forced the storm to the southwest. This took the center of Katrina through the Everglades, where it maintained its structure over the flat wetlands. Upon reaching the Gulf of Mexico on August 26, Katrina steadily strengthened. But that was nothing compared to what happened when Katrina reached the central Gulf and began her recurve to the north. Here, conditions were highly conducive, resulting in the explosive development of Katrina into a major hurricane. As it approached the Gulf Coast, Katrina lost some strength due to wind shear and reached the Louisiana coast on August 29th as a Category 3 hurricane. Rarely has the Gulf of Mexico exhibited such a favorable environment for a major hurricane as it did on August 28, 2005. As Hurricane Katrina moved into the southeast Gulf of Mexico, upper air winds over the central Gulf fell practically calm with just a light outflow from the region as indicated by the arrows in this satellite photograph. This was an ideal situation for Katrina since brisk upper air winds would have been hostile to the storm. When the upper air winds are strong, such as shown in this satellite photo of Hurricane Florence in 2006, the top of the hurricane is sheared. This disrupts the entire system, throws it out of balance, and results in a weakening or complete dissipation of the storm. On August 28, 2005, a near zero wind shear environment existed over the central Gulf. This light wind environment, now directly in the path of the storm, favored rapid intensification. To add to this, the central Gulf was exceptionally warm thanks to the presence of the Gulf Loop Current shown in red in this illustration. This river of warm water is a normal feature of the Gulf. Now watch as we view the Gulf Loop Current over the first 8 months of 2005. Whereas the water over most of the Gulf was warm during the summer of 2005, it was warm only to a shallow depth. However, in the Gulf Loop Current, it was warm with considerable depth. When a hurricane crosses the loop current, the churning of the sea surface fails to bring colder water to the surface. Any hurricane crossing this area would be like crossing warm bath water. Katrina was one such storm. Katrina reached the central Gulf on August 28th. In this illustration, note the increase in wind velocity as Katrina reached the loop current and then turned north around a high-pressure system over the east coast. The near-perfect conditions over the central Gulf resulted in Katrina's explosive development into a Category 5 hurricane. A hurricane with sustained winds now exceeding 170 miles per hour. Now let's get on board the Hurricane Hunter P3 research plane and see what Katrina's eye looked like when the storm was a Category 5 on August 28th. Although the eye of Katrina is clear above, numerous low-level clouds can be seen circulating around the interior of the eye below. Notice the dramatic stadium effect in the eye wall, a characteristic of an intense, well-developed hurricane. With Katrina reaching a Category 5 and displaying great symmetry, the storm was now building and pushing an enormous amount of Gulf water northward under the eastern semicircle of the storm. Katrina first reached the Gulf Coast at the Mississippi Pass in extreme southeast Louisiana. At that time, the maximum winds in the eye wall had dropped to a Category 3 hurricane. Importantly, the eye of the hurricane moved north across the marshlands of Plaquemines Parish, leaving the stronger eastern half of the hurricane over the open waters of the Gulf south of the Mississippi coast. In this illustration, the arrows represent Gulf waters being forced northward in the direction of the Mississippi coast and onto the continental shelf. To complicate matters, the Louisiana-Mississippi coast forms a natural concave shape with Louisiana on the west side and Mississippi on the north. What happened here? What caused the storm to be so massive? Why did the record storm surge cover such a huge area of the coast with hurricane-force winds reaching eastward all the way to Mobile? The reason for Katrina's massive size lies in a process that often occurs in the stronger hurricanes, but has occurred in weaker hurricanes. It is called the eye wall replacement cycle. Dr. Keith Blackwell explains.
The storm began what we call an eye wall replacement cycle, which is where the inner eye wall becomes surrounded by another eye wall. And this outer eye wall forms from a coalescence, if you will, or a merger of outer spiral bands of squalls. And so ultimately the storm will end up with two eye walls, one inside of the other, and there'll be very strong winds with each eye wall, which then means that the storm's wind field expands significantly as that outer eye wall continues to grow in intensity.
In September 2004, Hurricane Ivan underwent several eye wall replacement cycles as it tracked across the Caribbean Sea. Using microwave satellite imagery from the University of Wisconsin, we can see the double eye wall structure as the center of Ivan and the inner eye wall pass south of Grand Cayman Island on September 12th. Note the fading inner eye wall, while the outer eye wall remains strong. The outer eye wall hit the island directly, producing sustained winds of 150 miles per hour with gusts to 171 miles per hour. 95% of the buildings on Grand Cayman Island were damaged or destroyed by the outer eye wall. Now the question is, did Katrina have two eye walls? If two eye walls existed, this would explain why hurricane-force winds were experienced more than 100 miles east of the storm center and a record storm surge east to Mobile Bay. Is there any evidence of two eye walls in Katrina? The answer is yes. The first report of an outer eye wall was made by the hurricane hunters as they flew through Katrina on August 28th. A reconnaissance mission summary made a brief note of the existence of a second eye wall. Satellite microwave imagery clearly revealed the development of an outer eye wall. Watch closely for the formation of an outer eye wall as we trace Katrina across the Gulf with satellite microwave imagery. Note the intensification of Katrina, the inner eye wall, then the outer eye wall. Further evidence of an outer eye wall was revealed when dropson data from the hurricane was analyzed. A dropson is a canister that contains weather sensors and a radio transmitter. The dropson is ejected from the Hurricane Hunter aircraft, then descends by parachute through the storm. A few of the significant dropson peak winds are shown on this microwave image of Katrina as the eye neared the Mississippi coast on the morning of August 29th. Two of the dropsons were deployed into the apparent outer eye wall near the Mississippi coast. Dr. Keith Blackwell explains what was found.
Dropsons show that this outer eye wall existed as well. They vividly show it. Not only were they showing very strong winds within the inner eye wall of the hurricane, but then when the aircraft that was releasing these dropsons started dropping these instruments through the outer eye wall, they began to find eye wall winds out there with these dropsons, and at very low levels. What those reveal is definitely eye wall structure in the wind field. The dropsons south of Pascagoula found winds up to 142 miles an hour at 1,300 feet, or close to 1,300 feet. That's close to cloud base. That's right at the altitude where you expect to find your maximum winds in eye walls. And also the other dropson that was released south of Pearlington, Mississippi, shows a wind maximum of 143 miles an hour, a little above the altitude that the Pascagoula dropson showed, but still well within the range of where the wind should maximize in an eye wall. That's very, very convincing proof that this storm did contain two eye walls.
Although the outer and inner eye walls became open to the southwest as the storm reached extreme southeast Louisiana, the eastern and northern portions of both eye walls remained intense all the way to the coast. This resulted in hurricane-force winds occurring more than 100 miles east of the eye to Mobile Bay. In fact, the outer eye wall continued well into Mississippi, bringing destructive winds to interior cities such as Hattiesburg, Laurel, and Jackson. Hattiesburg was especially hard hit, with 80% of its roads made impassable by fallen trees. Note on this microwave image that when the outer eye wall reached the Mississippi coast, the entire coast was impacted. The outer eye wall produced northeast and east wind gusts well in excess of 100 miles per hour. The wind flow from the east and northeast actually opposed the buildup of water along the immediate coast, delaying the storm surge. In this waterfront view in Gulfport, Mississippi, easterly winds of hurricane force are blowing water to the west along the shore while the surge tries to move onshore. It was not until the eye made landfall near Pass Christian and Waveland that the wind became southerly along the coast and the maximum storm surge occurred. Notice the time of arrival of hurricane-force wind gusts on the coast, then the time of arrival of the peak storm surge. Because of the outer eye wall, the Mississippi coast was battered by hurricane-force wind gusts for several hours before the peak storm surge arrived. The western Mississippi coast was actually struck by two eye walls, with the maximum storm surge coinciding with the arrival of the inner eye wall. Watch as the outer eye wall arrives, then the inner. Many storms have produced areas of damage that far exceed the official Saffir-Simpson classification. But now it has become apparent that the outer eye walls and feeder bands of hurricanes are much more complex than previously thought. In this radar sequence of Hurricane Katrina as it made landfall on the Mississippi coast, notice the intense red areas in the eastern eye wall. These areas are known as collapsing cores. A collapsing core begins as a mass of precipitation suspended at 10 to 15,000 feet, well above the highest winds in the hurricane. Dr. Keith Blackwell explains.
These collapsing cores can be identified by looking at digital radar data from the Doppler radars, for instance, along the coastline. We can use 3D depictions. We can use various software to develop 3D images of the development of these heavy precipitation areas within the storm, up maybe at 10, 15, 20,000 feet above the ground. These collapses of precipitation down through this very strong wind in the eye wall can help bring that wind down to the ground in very, very strong gusts.
In Katrina, there were radar-documented cases of collapsing cores where highly destructive winds were brought down to the surface. In this image, the collapsing core is located at an elevation of approximately 3,000 feet. The collapsing core, shown in red, is located well above the maximum hurricane winds. The Mississippi coast is on the left and the Mississippi Sound on the right. Watch as the core collapses to the surface of the Mississippi Sound, dropping more than 10,000 feet in just 12 minutes. During its rapid descent, the core transported the highest hurricane winds down to sea level. In another three-dimensional view over Mobile Bay on the same morning, a collapsing core can be seen embedded in a feeder band over the eastern shore of Mobile Bay. From an elevation of 5,000 feet, the core, in red, dropped to the surface in just 6 minutes. This collapsing core brought winds in excess of 120 miles per hour to a small area along the Mobile River, more than 100 miles from the center of Katrina. Collapsing cores can contribute to the complicated damage pattern that results from landfalling hurricanes. In this microwave image, Katrina displays an open eye wall over the southwest portion of the storm as dry air enters the system. Research has shown that collapsing cores seem to be more common in hurricanes that have open eye walls, such as Ivan and Katrina shown here. Collapsing cores were not the only destructive wind producers in Katrina. Numerous tornado-like vortices formed in the eye walls and in the feeder bands over the Gulf and across Mississippi. Dr. Pat Fitzpatrick explains.
A mesocyclone is a rotating thunderstorm. We know about 20 to 30% of mesocyclones produce tornadoes. If you look at the radar imagery from Mobile, Alabama and Slidell, Louisiana, you see about 100 to 150 of these mesocyclones. But we also have a reason to believe that, particularly in the Mississippi coast, that some of these mesocyclones were also missed as well. The reason for that is the radars are not in this location. They are 50 to 100 miles away or more. And because the earth is curved, you don't necessarily see the cloud base. Most tornadoes and hurricanes are very low-level events. And because the cloud base is low, we know also probably a lot of these mesocyclones were missed as well as tornadoes.
Now let's take a look at each of these rotational features along the Mississippi coast and inland as detected by Doppler radar. First, tornado vortex signatures that show possible tornadoes. Next, mesocyclones or rotating thunderstorms. Now three-dimensional correlated shearing events that show rotation aloft with considerable depth. And lastly, other uncorrelated shearing events. As is evident from this map, there were hundreds of rotational features spawned by Hurricane Katrina, but not all of them were detected by Doppler radar. Many of these contributed or had the potential of producing major wind damage. You have just witnessed an in-depth study of a very unusual hurricane. Katrina was one of those rare hurricanes in which everything came together: the shape of the coast, the funneling of the storm surge, the extreme power of her winds, and most importantly, the double eye wall structure. For it was the double eye wall structure that made Katrina a monster storm and put strong hurricane force winds and vortices on the coast well before the record storm surge arrived. Then, as if that wasn't enough, Katrina produced numerous collapsing cores and rotational features that brought extremely high winds from aloft down to the surface. Despite a massive area of Category 5 damage in Mississippi and Louisiana, Katrina will officially go down in the record books as a Category 3 storm at landfall. Thus, Katrina clearly demonstrated that there is a serious flaw in the widely used Saffir-Simpson scale. We've come a long way in the last few decades in our ability to forecast and monitor hurricanes, and in the process, we have saved thousands of lives. But as is usually the case in nature, there's still a lot to be learned. As our research has proven, accurate assessment of the causes of storm damage requires post-storm analysis and evaluation of microwave satellite imagery, as well as a detailed review of all recorded storm data. By identifying and recognizing the power of the double eye wall, collapsing cores, and rotational wind events, it becomes clear that the winds of Katrina produced extensive damage before the waters came ashore. I'm meteorologist Dr. Bill Williams.